We had a war on cancer going back many decades, but we can't say we've cracked the problem. Cancer Moonshot is using new tools, using a new level of activity and collaboration to hopefully get that solution that's been so elusive for the last half century. A lot of people are surprised about the Department of Energy's interest and role in addressing something like cancer. Our national laboratories actually are the ones who started the Human Genome Project. We are now on the path, early in the next decade, to produce computers that will do 10 to the 18th operations per second. But we are also looking at applications of computers of that scale to big problems. Cancer is one of those big problems. It's really about managing enormous databases beyond human comprehension in a way that we can mine to get the secrets out to treating cancer. The computational community, those who apply computers to big applications, are going to be very, very central to cracking this problem in our society. We think this can be a revolution in how cancer is treated. People can go on and live their healthy lives with their family and see their kids grow up and their grandkids grow up, and I have grandchildren, so that's something that I certainly feel at a very personal level.
Please welcome your moderator, Steve Conway, IDC Research Vice President for High Performance Computing.
Welcome everyone. Thanks for joining us. I'm privileged today to moderate a session on a topic that is near and dear to me, both as an HPC community member and also as a former healthcare executive, the role of HPC in precision medicine. So let's have a definition first. The National Institutes of Health defines precision medicine as an emerging approach for disease treatment and prevention that takes into account individual variability in genes, environment, and lifestyle for each person. An earlier term for something like this was personalized medicine. Precision medicine promises to improve health outcomes while also curbing the rise of healthcare costs. Zeroing in on the most appropriate treatments for diseases improves the quality of care, and it also prevents unnecessary treatments that can compromise care and also boost costs. And curbing cost increases for healthcare is important. US healthcare spending amounted to about $3 trillion in 2014, and it's headed toward $4.8 trillion in 2021, according to the Centers for Medicare and Medicaid Services. Healthcare spending in many other countries is more in the 9 to 11% of GDP range, which is less alarming, but also pretty substantial. But the main goal of precision medicine is giving physicians and other healthcare providers tools to enable better health outcomes for patients. Zeroing in on the most appropriate care is really the goal. And IDC is already tracking dozens of initiatives around the world where precision medicine is helping to save the lives of children and adults who have exhausted the possibilities of traditional medicine. IDC will soon be, we at IDC will soon be adding precision medicine to the new HPC market segments that we track for commercial analytics that require the power of HPC. One major initiative you heard about in the introductory video and that you'll hear a little more about in the session today is Cancer Moonshot. That is a US program that aims to accelerate cancer research in this decade. But there are impressive precision medicine initiatives all around the world today. It's not just the US. This session relies on 5 distinguished experts with 5 different perspectives on precision medicine and the role of HPC in this emerging field. What's going to happen is each expert will briefly summarize his or her perspective, and then after that we're going to open up for a Q&A session. We have a couple of starter questions here, but then we will open up for questions from anyone in the audience, and there are microphones in the aisle, so I know this is not a shy crowd, so please come up to the mics and ask whatever questions you have. Our hope is that this session will provide new information and new insights on precision medicine as a new field of endeavor and also as a new market for HPC. Given the vast amounts that nations are spending today on healthcare, precision medicine promises over time to become a very large market for HPC. So now, let me briefly introduce our distinguished experts in the order in which they'll be speaking. And one note is that we have a substitution. One of our speakers, Dimitri Kusnezov from DOE, kind of his travel plans, he got kind of stuck in San Francisco. And Fred Streitz from Lawrence Livermore National Lab graciously, at the very last minute, agreed to substitute. So thank you, Fred, for doing that. So our first speaker will be Mitchell Cohen. Dr. Cohen is the Bruce Rockwell Chair of Surgery at Denver Health Medical Center and Professor and Vice Chair of Surgery at the University of Colorado. Clinically, he's an active trauma, general, and acute care surgeon, as well as a busy intensivist. In addition to his clinical activities, he's also a busy basic science and translational investigator, leading a large group working on coagulation and inflammation perturbations after injury and sepsis. He's worked in both dynamic modeling of biological systems and big data approaches to improving the care of sick and injured patients. So let's please welcome Dr. Mitchell Cohen to the stage. Our next speaker will be Warren Kibbe. He's the director of the Center for Biomedical Informatics and Information Technology at the National Cancer Institute. Through this center, NCI is helping to speed scientific discovery and facilitate translational research by using IT, informatics, and data science to address complex research challenges. Please welcome Dr. Warren Kibbe. Steve Scott is Senior Vice President and Chief Technology Officer of Cray, Inc. Steve holds 39 US patents and was the chief architect of several supercomputers and interconnects at Cray. He received the 2005 ACM Maurice Wilkes Award and the 2005 IEEE Seymour Cray Computer Engineering Award. And he's a fellow of the ACM and IEEE. Steve, please come to the stage. And our hero of the evening, Dr. Fred Streitz, substitute last minute, is Chief Computational Scientist and Director of the High Performance Computing Innovation Center at Lawrence Livermore National Laboratory. He leads projects that develop HPC applications, pushing the limits of computational capability, and guides Livermore's efforts to connect with industrial partners seeking computing solutions to their pressing problems. His multidisciplinary research teams have twice won the Gordon Bell Prize for significant achievement in supercomputing, and were finalists 2 other times with work encompassing the fields of material science, turbulence, biomedicine, and plasma science. Please welcome Dr. Fred Streitz. And finally, Marty Head is Senior Director of Insights from Data, the team working to embed data foundations, tools, and innovations widely throughout GlaxoSmithKline. Before this, she led the company's national team charged with applying computational technologies to GSK's therapeutic areas from target selection to candidate selection. Please welcome Dr. Marty Head. And so without further ado, we'll have our first speaker, Dr. Mitchell Cohen.
Great. Thank you very much. It is an absolute honor to be here in what I am sure is a mutual admiration society. One of these deals where I'm certain that every one of us thinks that we've got the best end of the deal. As mentioned, I am an active practicing trauma surgeon, acute care surgeon, general surgeon, so if you get shot, stabbed, or run over, I'm your guy. A very good person not to need. I also work in the basic science lab on coagulation and inflammation, and have worked for quite some time in data science and dynamic modeling. And I'm here to give the clinical perspective and the translational perspective of precision medicine. And now, of course, we're here to talk about precision medicine. We've been working in this space for quite some time. We've been calling it physiologic state recognition, this idea that the sort of clinical acumen that we want to model is that a patient sits in a physiologic state. That state has some propensity to transition through this state space. Hopefully they're headed toward health and away from sickness. And of course, our goal as clinicians is to modify that trajectory and to push them toward health and away from sickness. We've been working in this space for quite some time. People used to look at us like we had three heads. And indeed, the world has finally come to a maturity with the advances in high-performance computing, analytic methodologies, the ability to gather big data, and the understanding that this sort of prediction is ubiquitous, that all of our physicians and clinicians are being marketed to all day long on their iPhones while they're taking care of these patients. Now, of course, in medicine, we've been doing this for quite some time, and we haven't called it physiologic state recognition. We've called it clinical acumen. And indeed, that's exactly what, and I use this term affectionately and respectfully, the grizzled old clinician at the bedside is doing when he or she can look at two seemingly identical patients and say, you know what, this guy in bed 1, he's all right, but this guy, a woman in bed 2, there's something wrong here. This doesn't look right. It doesn't smell right. I've seen this before. That is physiologic state recognition. That is machine learning. That is pattern recognition, and we call it clinical acumen. And I'm here to tell you as a clinician that while I think much of the lay public thinks that they're going to get sick and come to name your famous hospital, name your famous ICU, and we're going to have the device, the tricorder, which is going to tell us what's wrong with the patient, it's not, in fact, that way. And indeed, you're going to do well if you have that experienced clinician at your bedside who can look at you and just intuitively know what's wrong based on their experience. If you get that person at your bedside, that doc, you're going to do well. If you get the bright-eyed, bushy-tailed, well-rested young trainee in the starched white coat who went to a movie the night before and got a good night's sleep, maybe you're not going to do as well because he or she just doesn't have that experience. And the question is, can we use computational modeling and high-performance computing and what we know about biology and physiology and the clinical trajectory of our patients to model that astute old clinician? Now, needless to say, we work in an incredibly data-intense environment. I work a lot of my my clinical day in the intensive care unit, where we have the most expensive, the sickest patients, but fortunately, they are the most highly monitored patients. Unfortunately, I will tell you that the current state of physiologic state prediction is not so rosy, and I'm here a little bit to set the stage of, frankly, why we need all of you to work on our problem and to help me take care of my patients at 3 in the morning. We take and monitor a tremendous amount of this data, but frankly, it just flows by us very quickly. Our clinicians struggle to keep up. In the middle picture here, there's actually a patient in the middle that's really hard to see, and you can imagine how computationally and cognitively burdensome that can be. Now, fortunately, I come from 2 world-famous institutions. I am extremely proud to be the new chair of surgery at Denver Health, an iconic public safety net and trauma center with a decades-long legacy of trauma and acute care surgery research, sitting in the academic behemoth that is the University of Colorado. And prior to that, I worked at San Francisco General Hospital, now called Zuckerberg San Francisco General Hospital, also an academic behemoth. And so we had the state-of-the-art of ICU precision medicine as of 2016. It's in this picture. It doesn't project super well, but so I drew a little circle around it. And it looks, while we talk at a high-performance computing conference, this looks an awful lot like a 4x6 index card with patient vital signs, some laboratory tests, some analytic notes about the patient trajectory written on it. And indeed, how we take care in modern medicine at name your big famous hospital of the sickest patients in the hospital is we have the most junior member of the team at 6:30 in the morning on rounds, read old, outdated, non-relational, often wrong data out loud to us. Then we examine the patient, and then we use our combined clinical gestalt to make patient care decisions on the sickest patients in the hospital. That's wrong. That's why we need high-performance computing. And indeed, our data guides how we think, talk, and treat. We treat one parameter to one threshold. We're fond of saying we keep it between the lines, and we're really treating univariately in a multivariate world. And the only multivariate analytics that's going on, again, is in the head of that astute clinician at the bedside. And if you get that astute clinician, you're going to do well. And if you get that less astute clinician, maybe you're not going to do as well in modern healthcare. What's wrong with this? Well, we'll talk a bunch about healthcare costs are soaring. There's a big problem, as outlined in this Institute of Medicine report, with medical errors. And indeed, even the Institute of Medicine report, which is a little outdated now, suggested a critical role for information technology and analytics in mitigating these problems. Precision medicine is all the buzz. I hope that the political winds keep blowing in our direction. Now I think that this is really a call to arms, that we as clinicians sit there at the bedside, and this can be true in the intensive care unit, it can be true in the operating room or the emergency department where I spend most of my clinical life, but it also is absolutely applicable to population health, it's applicable to cancer health, as Dr. Kibbe and others are going to talk about after me, and it's appropriate to our primary care colleagues who are dealing with big population health issues and trying to figure out which of their patients need to come see them, be triaged into further medical care, and which patients probably don't even need their checkup this year and can wait until next. So our cancer colleagues have done wonderful things with precision medicine, and we're going to talk about them a little bit. And indeed, the idea that we can sequence the omics of our tumor, and we can sequence the omics of our host and understand that relationship and figure out which therapeutic your breast cancer, your colon cancer is going to be amenable to is outstanding and extremely important, and the Cancer Moonshot is magnificent in every way. But I have a hope, and my hope is that we look back at that several years from now and we say, well, that wasn't really precision medicine. That was kind of like better pathology, somewhat akin to saying, well, we used to look at tumors grossly, and then we got this cool thing called a microscope, and then we got stains. And that I hope that the real future of precision medicine is, again, identifying where our patient is at any given time, their physiologic or biologic state, and where they're going to be in 2 minutes, 2 hours, and 2 days, and then providing decision support back to our clinicians to allow us to modify their trajectory toward health and away from sickness. Fortunately, the world is not so dark, and there have been great strides made in several of these areas, outside and separate from the wonderful cancer work that Dr. Kibbe is going to talk about next. And that includes visualization of high throughput data, understanding of our biologic systems, and I think the beauty of high-performance computing is it can sit in that chasm between model-driven basic biology and data-driven prediction. Actual state identification where we can indeed do exactly that, start to model the head of that astute clinician, understand where our patient is in their state space, and predict before we can even realize it as clinicians that our patients are transitioning towards sickness and allow us to intervene earlier and ultimately save lives. And that, I think, will be the future of precision medicine, and indeed why this multidisciplinary group on this stage and represented in this audience is so incredibly important. I'm extremely excited and proud to be a part of it, and I look forward to the question and answer session at the end.
Thank you. Thanks, Mitch. Okay. Next, we'll hear from Dr. Walter Gibby.
Uh-oh. There we go.
go. All right, it's great to be here. It's wonderful to see all of you and to get a chance to talk a bit about the Cancer Moonshot in particular and how we've been thinking about really trying to apply precision medicine in important ways to cancer. Since I'm from the National Cancer Institute, I thought I would tell you a little bit about our mission very briefly. So we are the part of the federal government that's job is really creating the scientific evidence base for understanding cancer and for understanding how we can take that evidence and lessen the burden of cancer in the United States and, of course, across the whole world. So I also want to give you a little bit of the statistics so you understand how important it is. I think we've all been touched by cancer in different ways in our personal families. But to put some numbers on it, in this year, the ACS estimates there'll be 1.7 million new cases of cancer in the United States alone, and roughly 14 million, a little bit more than 14 million across the world. And in the United States alone, 600,000 people will lose their life to cancer. So again, it's a really important struggle. It's a really important disease for us to understand. And the good part is that we are understanding it in fundamental ways. And in fact, the mortality rate in cancer has been declining every year since about 2000. So we are doing some things right, but it's clear, again, back to what Steve mentioned about precision medicine, we need to understand more about basic biology. We need to understand more of the complex interplay between biology, cancer, and in fact the data that we generate in the clinic, in labs, and across the whole country. And so that's the essence, at least in my view, of precision medicine. And it is absolutely, to what Mitch said, it's more than just genomic data. It's got to be proteomic data, imaging. It's all the things that happen around each of our lives, and we need to understand the impact that has as we develop cancer. So cancer itself is a grand challenge. For us to truly understand it, we really have to understand fundamental biology, fundamental processes that right now we only get the simplest glimpse of. And we need, of course, new methods to help us address problems in cancer. We need better instrumentation. We need better technology. And of course, we need advances in computation, which is why, again, this audience and this plenary is so incredibly important. It's an opportunity for all of us to start to come together and really understand how do we model, how do we predict cancer in a very different way than we've done it up until now. So I mentioned the Cancer Moonshot. There's several pieces to it. I'm not going to bore you with all the details. I will say that I feel like the last year or so of my life, hasn't been quite a year yet, I've been riding on a rocket, but I was stuck on the outside. They didn't let me in. So the Cancer Moonshot's been a very exciting ride for me personally. And at the end of the day, it's really about making data available to all of you to do interesting computation, to make interesting observations, and make that data available to all kinds of researchers across the country. And one big piece of that has been the Genomic Data Commons, and I want to give a shout out to Bob Grossman and his team in data intensive sciences at the University of Chicago. They've really done the lion's share of building of the Genomic Data Commons. They're at booth, I believe it's 2611. Please go and visit them during the exhibit. And of course, it's not just about the Genomic Data Commons, it is about all these other data types. And it's also about how do we take data out of existing repositories and get it into the cloud so people can use cloud computing more effectively. And it's also been part of the joy in the last year for me has really been working with colleagues at the Department of Energy, some of their collaborators, the national labs, and understanding what the tools and the power that they can bring to these problems. And Fred will talk a little bit more about some of those projects. And it's also been building up public-private partnerships and working with GSK and DOE. It's been really important too. And again, we think that as we start building a bigger and bigger community where we can really engage everybody, we've done something fundamentally different and fundamentally useful for cancer. And as you see, it's audacious yet possible. That's at least one of my bylines. I don't think that's anybody's official byline for it. But we really want to use real-world data and have every patient's data across the country, across the world, be accessible from a prediction standpoint. So this is a slide, actually it's a screenshot of the Blue Ribbon Panel recommendations that were part of the Cancer Moonshot. There are 10 scientific recommendations that more than 150 experts from around the US got together in a very short period of time and laid out the 10 best ideas that we think we can accomplish in the next 5 years. So I encourage you to go to cancer.gov/BRP for Blue Ribbon Panel and read those recommendations. There's both a very short synopsis, a longer version, and then the really long 150-page document that, again, if you're interested enough to read that, I'd really encourage you to go there. And I think with that, I will turn over the stage.
So thank you, Dr. Walter Gibby. And next speaker is Steve Scott from Cray.
It's wonderful to be part of this incredible panel. These are all the people that understand medicine. I'm the computer guy. Precision medicine brings together a growing set of disparate data to better understand the unique situation of the individual. There's, of course, patient data, the patient about the data in question. This could be the patient's genome, the clinical history, the tests, the scans, the lifestyle, the environment. But then this is coupled together with a vast amount of community knowledge, data about the population as a whole, the entire medical literature, clinical data, drug databases, disease databases, experimental data, et cetera. And then using high-performance computing, we can take all of this data together and mine it for the long tail of the distribution to better concentrate on the individual instead of the average. There has been a lot of work in this area. One of the more interesting projects that we're aware of is a group at Harvard Medical School that have been working with the supercomputers at NERSC to look at cancer mutations. Now, humanity understands a large number of cancer mutations. We have databases filled with a vast number of cancer mutations. And historically, what we've done is looked at the most common mutations and scrutinized those and studied those and developed medicines and treatments for those common mutations. And that gives you good treatments for the average patient. What this team did instead is using the supercomputers, they went through the entire database of cancer mutations, and they used detailed statistical mechanics simulations to look at the atomic level interactions between the cancer mutations and the proteins to see how those mutations impacted the complex social network of the proteins. And they found some surprising results. They found that rare mutations are about equally as likely as the common mutations to affect the protein networks. And they found that they affected protein networks in some very subtle, indirect manners. And these sorts of understandings then can lead to precision treatments that are targeted towards individuals, the long tail of the distribution. Another great example of using this vast amount of data is a group at Oak Ridge National Labs who created a piece of software called Origami, which mines the entire set of 23 million medical papers, research papers, that have been distilled into a vast knowledge graph. And they built scalable software that's able to do complex pattern matching in this graph database, as well as some fairly sophisticated reasoning. And using this, they can answer some relatively complex questions about diseases and drugs and treatments. And in fact, they were able to use this same technology to help diagnose some people with very rare diseases and conditions. So this is the sort of thing that can be done with this vast amount of data. Now, we computer scientists tend to like to talk about gigabytes and petaflops. We write MPI applications that are written in C++ and Fortran. The emerging data analytics world is a bit different. They tend to use different programming models such as Spark and Scala and R and SQL, Python, etc. And so this causes a bit of a disconnect, but the real disconnect is between the entire computational and computer science world and our clinical scientists and physicians. What we really need to do is build up solutions that, that those people can use. Now, the computational demands and the complexity of the algorithms and the growing data sets are pushing us to build larger and larger machines, more capable machines, like the Cray system that was recently introduced at NERSC. Fortunately, it's pushing us in the same general direction as the broader HPC community is. Computation tends to get all of the attention, so people talk about how many flops you have. Computer architects know that the real way to build a supercomputer depends upon the memory system and the interconnect. Effectively, the supercomputer's ability to move data. So the things that we're doing to build ever more capable supercomputers tend to be quite well aligned with processing the vast amounts of data, as well as doing the coupled simulations that go into precision medicine. We see something very similar in the software side, where common HPC techniques like simulation work that's done on molecular dynamics or finite element analysis or image processing can be brought to bear fairly successfully on precision medicine problems. And we're also seeing precision medicine pushing us in some similar directions to some new areas like large-scale graph analytics and machine learning. So in general, I think that the direction that they're pushing us is quite well aligned with the direction of other disciplines. So as I mentioned, what we'd really like to do is build solutions that actual practitioners can use and not have to be computer scientists. One of the early collaborations that Cray has had is with the Broad Institute. We worked with them on the development of what's called the Exome Aggregation Consortium, or XAC, database. This is a database that contains the exomes of over 60,000 different people. And they put it all together in a searchable database where an individual clinical geneticist can take the genome of a given patient and then compare it against the population's genomic database and see where there are variations with the general population. Are those variations rare or are they common? How likely are those variations to have an effect on diseases, et cetera? When they made this available online, it got immediate and enthusiastic uptake, and it's being used broadly as we speak. This is the sort of collaboration between HPC system providers and technology providers and the leaders in the healthcare industry that we need to see more of. And it's really illustrative of the type of co-design that we've done historically in other areas. We really want to build systems that can work well to solve problems. And we really look forward to continuing this level of collaboration in the future and staying very, very highly engaged in the precision medicine community.
Thanks to Steve Conway. Steve Scott. Thanks to me, too. And the next speaker is Fred Streitz from DOE's Lawrence Livermore National Laboratory.
Thank you. Well, it is an unexpected privilege to be up here. But I never shy away from an opportunity to describe a little bit of what we're doing to build these collaborations that are so exciting. And it's a special honor and pleasure to be up with my colleagues and partners in crime with which I'm working with over the last couple of years to build these relationships. The collaborations we're building, I think, have the opportunity to really affect all of us in very profound ways. We say that HPC matters. I mean, and we know that's true, not just because it said so in big letters when we walked in, or that we tweet #HPC matters all the time. We live that. We breathe it. We feel that every day. But that's us. That's this community. We know in our hearts that HPC matters to a lot of other people apart from us. But that isn't always easy to point out. I mean, we come up with stories that explain the development of the iPhone or the creation of a Boeing jet or whatever. But we're about to change that. The application of high-performance computing to, for instance, accelerate our understanding of cancer, or to revolutionize the design and delivery of therapeutics to a public, that's game-changing. If we can accomplish that, HPC will matter, and it will matter to everybody. So the DOE has really a very long history of applying high-performance computing to solve problems. Extreme scale computing to look at some of the most challenging problems in science and national security that we face. In doing so, we have built a very robust ecosystem of tools and applications, of experience and know-how, and partnering with experimentalists closely in order to be able to build solutions to the problems that we face. And we solve those problems using computing. That's something we're familiar with doing. The President's National Strategic Computing Initiative sort of implies that we're going to continue to do that. It says very clearly that it is an imperative to the nation that it continues to push forward an agenda of higher performance computing, that's important for the competitiveness of the nation. And it identifies the DOE as one of the lead agencies responsible for developing applications and hardware that enable that. It also, in a whole-of-government approach, suggests that there are broad deployment agencies, of which the NCI and NIH are one, that could benefit from that experience and that expertise, and that they're encouraged to partner together. Think about that, partnering among multi-agencies in the government. What would happen next? So it seems reasonable then that as the NCI and the DOE were talking together, that we came to the conclusion that what more important problem to work on than cancer? And so in conversation with our partners at the NCI, we identified 3 pilot programs that would start attacking this, looking at 3 different scales of the problem. So the first pilot is at the cellular level, and it's trying to develop predictive models for preclinical screening. And what it really is trying to do is make sense of the gross heterogeneity in response that we see in cellular data on, from the response of cancer therapeutics. So if you give a drug to a particular cell line, even a cell line that is ostensibly identical, you don't get identical results. If, for instance, you have cancer and you do a biopsy and they take that biopsy and implant it in a mouse cell, in a patient-derived xenograft, and then they generate several mice that all have ostensibly your identical tumor and then treat those mice, you don't get the same answers. We have, however, developed a fairly large database and a very large growing database of all of these responses. And so Pilot 1 is focused on using machine learning to not only uncover what we hope are the predictive patterns in that data from the preclinical data, but also to use machine learning to help develop optimal experimental strategies so that you don't have to do wide surveys. You can actually do targeted surveys and get to predictive responses quickly. Pilot 2 is focused at the atomic level, at the protein level, a much smaller level. It's focused on RAS biology. So RAS proteins are ubiquitous proteins in mammalian cells. They're responsible for, among other things, cell growth. And as you might imagine then, there is an oncogenic mutant of the RAS protein that winds up allowing that protein to get stuck in an on position and causes unconstrained growth. It's responsible for about 30% of cancers in humans, including some of the really, really ugly ones, pancreatic cancer, lung cancer. These are cancers for which there are no cures and which move very rapidly. So the focus of pilot number 2 then is to look at using molecular dynamics techniques that we're going to have to develop novel molecular dynamics techniques to look at RAS biology on a membrane to answer some of the fundamental biology questions of how RAS behaves on a membrane, because that's where it works, that's where it's important, and to identify targetable areas where we can then develop therapeutics. The third pilot is really where the rubber hits the road. This is focused on the population scale. And its focus is on developing an effective national cancer surveillance program that takes advantage of all of the data that we currently have, that we're already collecting in the various statewide surveillance programs of everyone who has ever had cancer, and what happened to them, what treatments did they get, what was the outcome, how did they respond, all of that. All of that's captured right now. But it's captured in very different ways in very different states, and trying to understand that data in order to put it into a database that would actually allow you to do something useful with it is a major, major challenge. That's pilot 3, is using first natural language processing to make sense of the data and regularize it, and then to use machine learning to actually extract information in in a way that would be useful. So there are two key elements that combine all of this. One is the increasing importance of data analytics and machine learning in combination with predictive simulation. I don't think of those things as that distinct anymore, and I think that when we're done developing the next generations of hardware, they will not be distinct. The combination of those two is going to be extraordinarily powerful. That's true in all three pilots, and it's true in our thinking of how we're approaching this. The second thing, and this is what I'll leave you with, is the importance of partnership. I think even in the year that we have been working together, the partnership between the scientists inside the labs and the scientists, their partner scientists at the NCI, actually doing the work, the bench scientists, getting them to talk to each other. What are the problems? What can you measure? What can't you measure? How hard is that? What can you simulate? What can't you simulate? How hard is that? That conversation changes how you view the problems and is how you make progress. That ability to put people together across multiple stripes is how you win. And that's what we intend to do. Thank you.
Thank you very much. Thanks. And next we'll hear from Dr. Marty Head from GlaxoSmithKline.
Hello, everyone. You heard it in Secretary Moniz's comments in the opening video. We often think of disease as a war, as a battle against an invader that is attacking our bodies. But that's an imperfect metaphor to explain what disease really is. Even in the case of trauma with a knife or a gun, or in an infectious disease, it is often the response of our bodies that causes the real damage, that is the real disease. And in something like cancer, although in a mouse xenograft model we think of it as a tumor that is coming after us, really disease, really cancer, is a function that is intrinsically part of who we are. It is part of our genetics, it is part of our physiology, it is part of the environment in which we operate and move. And that is why we need a transformation in the way that we discover drugs and deliver them to our patients. A transformation that understands and takes a holistic approach to all that I am as an individual and how that contributes to throwing my body out of homeostasis and away from health and towards disease. You've heard from all of these my distinguished co-panelists about the increase in the data that we have available to us. Genetic data, data from cancer records and health records, the data that's locked up within pharmaceutical companies like my own. And so there's large amounts of data, but even more importantly, those data are complex. They're complicated. They are on different scales. And that is why we need a transformation in the way that we discover drugs and deliver them to our patients. A transformation that allows us to combine all of those types of data that gives us insight into the wholeness and the holistic view of who I am as an individual and how that leads to disease. And finally, the drug discovery industry is facing a crisis at this time. It takes us 5 to 7 years to go from a disease hypothesis to a candidate that can go into the clinic. And then we still have all of the years of running a reliable clinical trial before we even understand whether that disease hypothesis has any holding, is any truth, whether it connects to that understanding of us as a human being in any way, shape, or form. And if we are truly going to achieve the vision of precision medicine, of finding treatments, of progressing the work that our physicians do at this individual level, we have to go faster than that. And we're not going to go faster just by taking the same processes that we're already doing and shrinking down the white space and just rushing ever faster. No, this is why we need a transformation in the way we discover drugs and deliver them to our patients. A way that takes a new approach that combines the simulation and high-performance computing, the data analytics, and combines experiment in a new engineering paradigm that almost treats an experiment as a subroutine or a function in a larger algorithm that we are running in our drug discovery process. This is why we need a transformation. And this is why high-performance computing matters. And so I, as a member of GSK, am excited to be working with the NCI and the Department of Energy and Lawrence Livermore with the Atom Partnership, a Cancer Moonshot project that will bring together all of these data sources, all of these ways of computing, and the experimental know-how and the data from the pharmaceutical industries to drive towards an audacious goal of going from disease hypothesis to a treatment that can go into the clinic, not in 5 to 7 years, but in 1 year. That is why high-performance computing matters.
Thank you. Thank you very much. Great. I'm going to move into a questioning area, and what I really would like to do around the panel here is to talk about some of the challenges from each of their perspectives that they see toward making precision medicine a norm in the future. And I really would like to start with you, Dr. Cohen. Can we talk about the physician-patient relationship and things like, in order for precision medicine to be real with the help of HPC, does it have to operate in kind of real time in the office while the patient is still with the physician?
Yeah, it's a good question about how, the leap from HPC to the actual physician-patient relationship. And I think it can work in many ways and on many scales. Part of it really just provides decision support and is really a statistical transform in some sense, from all that biological knowledge and that data into some sort of decision support. I periodically get a little bit of pushback from my clinical colleagues when I talk about these issues, and they say, oh, you're talking about autonomous computing, and the art of medicine will be gone and I'll be replaced. And I don't think that that's true. I think there's so much unmeasured and unknowable data and confounding that really what we're talking about is providing additional knowledge, which allows us to then use our clinical gestalt of a particular situation to take better care of the patients. That's on the one hand. The other sort of half of that answer to that question is how it works. Sometimes it is a cancer therapeutic that's being developed as a result of this big data. Sometimes it is continuous prediction on continuously captured data at 3 in the morning in the emergency department or the operating room or the ICU that's going to help us understand what that physiologic state is. And I think that, not to talk about the HPC space that I'm not an expert in, but that's an interesting computing architecture problem of what should be run on the big high-performance computers and what can be computationally tractable to do at the bedside in real time. And I think that infrastructure, that data reduction or dimension reduction, is a particularly interesting topic.
Okay, thank you. And the next kind of natural follow-on to that, Dr. Head, is about, you kind of alluded to the great volume and complexity of data. Do we have enough data? Where are we?
I have friends in the computational chemistry community that I came from who are quite vociferous in reminding me that when you compare us to Google or Facebook or Amazon, we are not working in big data. We are working in minuscule data. And when you start thinking about trying to understand precision medicine at the level of the individual, and we have only a few hundreds of thousands of genomes available to us now, there is a huge gaping hole in the amount of data that we have available. And the challenge for us is to understand what are the questions we're trying to ask, what are the true problems we're trying to solve, and to find as many creative ways as possible to fill the data gaps, whether it's through partnerships across the pharmaceutical industry, finally releasing our data in ways that can allow it to be capitalized on, whether it is the 1 million-person cohort that we're trying to generate as part of the Precision Medicine Initiative. Understanding where those gaps are and in trying to fill them is as much a part of achieving the goal of precision medicine as all of the fine work that all of you in this room are doing. Without that data, you have nothing to operate on.
Okay, thanks. And Dr. Kibbe, you talked about Cancer Moonshot program, which, if I understand correctly, that's really aiming to accelerate cancer research in this decade. How far do we get in this decade? I know that's a difficult one to answer, but I mean, is this a 100-year problem? Is this a 20-year problem?
Well, so I think seeing, and I think this, Mitch said it already, is that the data that we already are generating can, if we use it appropriately, we can make advances with what we're already doing. Solving cancer as a problem, though, is something much more fundamental. It really requires us understanding fundamentals about biology, and we're not even close to that. So there are some truly monumental problems in front of us to be able to address really everything in biology. And cancer, as a disease, no two cancers are exactly the same because it evolves and it adapts to us. And for us to understand how that happens and how to really come up with the best possible therapies, we need tremendous amount of data, and we need much better predictive models than we currently have. So there's a lot of changes that will happen. But I guess I'll say in the short term, it's what can we do with the data we already know how to generate. There's lots of things we already know how to do. We need to be better at doing them. I hate making predictions, how fast we'll get there. But I feel like we are on a great trajectory. And again, part of the Cancer Moonshot is saying what pragmatically can we do today that we don't need to wait for 5 or 10 years, that if we start doing now will really impact patients' lives in 5 years. And that's the essence of the Cancer Moonshot.
Can I make just a clinical comment to that? I think the ultimate moonshot, whatever it is, cancer, physiology, all of precision medicine, will quite literally fundamentally change, a paradigm shift in the way that we practice medicine and save innumerable lives. But each incremental step literally today helps us at the bedside, right? Helps us as basic scientists really understand our biological models, but then really helps our clinicians save lives today. These are not, far off goals where we have to solve the entire prediction problem or get all of the data. Even a small incremental step in prediction or understanding of the fundamental biology translates directly, literally tomorrow, into the clinic, into better care of the patients and ultimately lives saved. And so I think we shouldn't forget those incremental steps are incredibly important, and there's really something for everyone, day by day in this.
Thank you. Steve Scott, what are the implications, if any, for the way HPC systems are designed? There's a lot going to have to happen in memory, not what?
Yeah, well, it's true that the data sets that we're talking about are not truly that large compared to the data sets that the HPC community traditionally has dealt with. But this is the poster child for systems that are good at data analytics and machine learning and traditional simulation all wrapped into one. If we just think about the genotype-phenotype mapping problem, that is a machine learning problem that is a grand challenge scale problem, just from a machine learning informatics perspective. And then you try to throw in all of the physics and the chemistry and the biology and have different disciplines and different time scales and wrap them all together. And there's just a tremendous computational explosion. So building systems that are good at all of these things and at the core are really good at moving data efficiently is going to help drive us forward. I think it's a great leading contender for that kind of system.
Okay, and Fred Streitz, you have a user community at Livermore that is working in a broad range of science, including biosciences. How much of a shift is this for your user community, or have they already shifted?
They are shifting, I think is the right way to, am my mic on? I think they are shifting.
Yeah.
Oh, now it is.
Okay.
So I wouldn't say they have shifted, but they are shifting. I mean, this is an
And is that difficult?
Well, for some people, yes. Change is always difficult, but this is the future, right? I mean, and I said that in my comments, and I want to echo some of the comments that were made earlier. The challenge in the biology space, from a computing angle, is that the equations aren't known, right? It goes back to what Warren said. We don't actually know a lot, and one of the things that's clear when you go to do a model about something, you try to build it on a computer, is that there's no way to hide. I mean, you find out very quickly what you don't know, because all of a sudden you need to write the routine that says, and now the magic happens, and there's nothing there. But that means, and that goes back to Marty's comment, that you start asking the right questions. Well, what don't I know, and what do I need to do to get what I don't know? And so now you start pairing the questions of what data you need. So that whole methodology is getting built into how we build computer programs now. And this notion of trying to solve fuzzy problems, heuristic problems, problems that are hugely stochastic, and understanding how that works, building in machine learning and data analytics into the prediction, that's now a hardware as much as an algorithm problem. What are the right machines we need to build that enable us to do that kind of work? The DOE is not likely to get into the cancer business precisely over the next decade, but it is going to continue to be in the computing business. And these workflows that we're developing, which are very novel, are not relevant only for biology. They're relevant in a vast amount of space. And I think unlocking where we can go with computing to look at these fuzzier problems and start addressing them, I think that's going to be very powerful.
Well, okay. And I'd love to follow up on this concept of user communities shifting. Coming at it from another perspective, I've spent my life at GSK working with chemists and biologists and crystallographers who come at life from a biology or chemistry perspective, and for them, it's an equally big, if not bigger shift to start moving towards computation and understanding how those two things can knit together, the science I do with the computation I do, much like your remarks earlier, Mitch, around how the physicians feel about that.
Okay. We have, I think, time for one quick more question, and the question, I think, we'll go to you, Dr. Kibbe, which is, can you talk a little bit about, how much more closely the communities that are represented here, in your opinion, have to collaborate with each other?
Well, I think that's a wonderful question, because it's in fact the whole reason why we're all here. Is the time is really, well, I won't say the time is now, but this is a great time for us to all be engaged between high performance computing, the different kinds of computational analysis, and people who are really working either at the bench or at the bedside. So how can we really bring everybody together as a community? Been working with DOE to bring that kind of computational scientists to the table, working with GlaxoSmithKline, and of course lots of other private industries to bring them in to say, well, how do we work together more effectively? I think the time really, in many different disciplines, it's obvious we need team science, and those multidisciplinary teams are a big deal. I think just from a workforce development standpoint, I'd love to see more people that are what I've been calling, and it's not just me, but a number of folks have been calling PI people, where you're trained in some kind of biological science, and then you're trained in something that's very quantitative in computation, in physics, in chemistry, and you bring those two things together through if you will, a breadth of experience. And those people then become glue in these multidisciplinary teams. So I think this is a great opportunity for all kinds of folks to get involved in cancer, in biomedicine in general. And I think your point about $3 trillion moving towards 5 is pretty, we need to somehow change that.
So I thank you, and I think we've come to the end of our appointed time. We want to make sure you get on to the next thing. But I want to thank our speakers, first of all, and the audience for your patience. And I think, I'm sorry we couldn't get to audience questions. If anyone does have a question, I think our speakers will be around for a few minutes here so you can ask. So please, I invite you to enjoy the gala exhibit opening next. Thank you.